we are thinking beyond blockchain.
This is the noob's perspective.
Can a person have duplicate IDs?
So when the function automatically returns, because that's the last line of the function, the value or the value of this value variable has been set from the state.
Yeah.
Okay.
This even happens in Solidity actually.
Correct. So now looking at this, what do you think exclamation mark does?
Exclamation mark.
Exclamation mark basically tells that it's a kind of it's basically for deployment.
But it's happening on okay, yeah, good point. Let me fix that problem for you. Now tell me what you want to think.
Yeah, got it. So like this exclamation mark basically tells that some value is being set, like a write operation.
There's a mutation happening. Yes.
Okay.
So it's like a Ruby. It's a Ruby style danger function. Okay. It means that function mutates state. Be careful here. Okay. So it very clearly tells you, even in the call set, no, you don't need to depend on whether it's the mutable keyword or the payable keyword. If the $sign is there, something happening here, be careful.
This exclamation, right?
Exclamation.
And then $sign for payable.
So you just do set $sign and that's for payable functions.
Okay.
There's also double exclamation. The double exclamation is for ephemeral, but yeah, that we've not decided yet.
There is no exclamation mark. That means like we are
it's a pure function.
Pure.
It's a pure or a view function.
View function.
Right.
Which means it's not modifying the state of the
It's not modifying state. It's only reading or may not be affecting state at all.
So this basically this arrows actually help
directional. Yeah, managing the direction, right? So then explain to me why in init there is an exclamation mark.
Where? In init.
Yeah, deployer init. There's no mutate statement there, but it still has an exclamation mark. There's nothing to think. It's a deployer. Deployers have to have exclamation marks because they're always about persistent state. Right?
Okay.
The exclamation mark does not say there will be a state transition. It just says there may be.
There may be. Okay.
Right. So a deployer by default is a constructor for a persistent state. Therefore, there is always a chance that something. So every deployer must have an exclamation mark, regardless of what is inside. But invocables, if they have a mutate statement and they affect persistent state, they must have an exclamation mark. Right.
So this is from an auditability standpoint, I'm guessing.
When an auditor wants to look at code, when the first thing you want to go take a look at is where are all the exclamation functions. I'm going to go look at all the exclamation and dollar functions and say, okay, what's happening here? Make sure that code is perfect. Similarly, now, when I call a function, that function also might have an exclamation mark, meaning it's mutating state. So at the endpoint, I can go and verify which functions are just reading functions, which functions are mutating functions. And I can go deeper and investigate the mutation functions. So as an auditor, I know immediately where the problems are. And even better, if I want to find out where all the modifications are happening, modifications always happen. You can just grep mutate and get all the mutate points.
Yeah, sure.
Right. So that's the other part of the security, right? You can say exactly where all functions mutate. When you deal with assets, there'll be another action called transfer. So you'll use transfer and you'll use. So when I want to deal with where money is moving, I can just grep transfer and find out where all money is moving. Right. So this is a good way for auditors to immediately detect what's happening with their code, right? So now we're noticing firstly that this mutate, right? When you see mutate init is mutating this and mutate new is writing to flip a state. So these are repeated code, right? So let's maybe use a chance to use a set function, right? So I can now go and write the set function here, right? It's a func set, takes a value and mutates and sets the value. That's all, right? Now I can use this set function repeatably in my invocable set here and over here. Got it? Good. So I have a function set which I'm reusing in both seed and in set.
Sure.
Clear? This makes sense, right?
Yeah.
So get set is very clear, right? Now, what is the
second set is not public?
Set? It doesn't matter if it's public or not. All functions are private. Okay. Functions by default are private. The capitalization that makes no difference. Okay. It's capital. That's just an aesthetic thing. Okay.
The keyword invocable, like what does it convey?
Keyword invocable means it's a call site that you can call. So there are, like I said, there are 4 types of calls. Okay, there's deploy calls, invoke, interact, and enlist.
Okay.
So deploy calls are used to create the logic and deploy the persistent state. And enlisters are used to on an existing logic create my ephemeral state on my account.
Okay.
So construct the ephemeral state on my account. So before I start working the logic, I need to enlist myself. So the logic can use my state. Then you have an invocable, which is just me and a logic. I'm a sender, OX Manish, talking to a logic. That's it. In an interactable call, there's OX Manish and there may be X number of participants. So I can pull in multiple accounts in and they'll all be available in the network, just in the thing. Right? So interactable calls are like multisig, force multisig. Okay. So in interactable calls, you can enforce that the other participants need to multisig, or that they don't need to multisig, they can just be brought in. Okay. So that depends on the interactable call. That interactable call design is still kind of fuzzy for us. We're still figuring that out.
What if no keyword is mentioned, like in case of second set?
Give me an example. What do you mean?
Like in the function set, there is no keyword like invocable, interact, like, so what?
Instead, you just do endpoint and then don't invocable, you mean?
No, I mean like in the function, not the endpoint.
Functions don't have invocable, all that. Functions are just functions.
Okay.
They don't have...
because they are internal. Right?
They're internal.
Okay.
They don't have deployers, invoke. All that is not on functions. Those only apply for endpoints.
Okay.
So the functions are just a reusable piece of code that you can call multiple times.
Okay.
Right? So functions can call functions, endpoints can call functions, but endpoints cannot call endpoints.
Okay.
Right? So this is simple. So we have most of our contract. We're obviously just missing one last function, which is the flip function. Okay? And this one gets interesting. This introduces the other last paradigm. Right? Who can take a look and see what's happening here?
The flip, right?
Yeah. Take a look at the flip function.
Actually, flip a state value actually comes to this value, mutate.
So the goal of the flip function is to, whatever the value is in state, reverse it.
Okay.
If it's true, make it false. If it's false, make it true.
Yeah.
Right? So what's happening in line 19 is, notice that mutate, usually we go from right to left. So left to right. But here, our mutate is doing the reverse direction. So what we're doing is, we're actually first reading the state value into this local variable called value, and then we can modify value how many ever times you want inside the indentation. So notice mutate here as an exclamation thing, it's indented.
Yeah.
So inside the mutate, it's called the mutation context. So in the mutation context, you can modify a value how many ever times you want. Whatever the final value of value is, gets written back to flipper.state.value.
So like we declared a variable right here, mutate value.
You know,
this is a local variable.
It's a scope variable, only available inside the indent.
Yeah. Okay.
It's available only in the scope. So if I try to do, print value, this would throw an exception. Print. I'm just giving an example, right? Because the value doesn't exist. It's outside the scope, right?
Okay,
the value keyword, value variable only exists inside the 20 and that key inside an indented key space.
So what is basically happening is
it's not changing the global state.
It is.
It is changing.
But first, it reads it to a local variable.
Okay.
And after that, in that local variable, you can do whatever you want. So I can do value equals this. I can do value equals false.
Value plus.
And then I can do value equals blah, whatever. Like, I mean, this. I can value equals. I can't change the type, but yeah. So I could do whatever I want here.
But in order to do it, like we have to put the right arrow, right?
You don't have to. That's the beauty of the mutation context. It's indented, okay? So the beauty is, because it's indented, the goal is whatever you do inside the indentation, you can make whatever changes you want. Whatever the final value gets written to the state. So the arrow will flip at the end.
Okay.
So first the arrow pulls and then it returns back. So it's like if you've written Rust code before, it's like borrow. Okay.
So this one is like the state value actually comes to this local variable, and then this local variable
can be modified inside the scope.
And this here on the left side is also the local variable. And
we're flipping the value. Value equals the reverse of the value.
Okay, fine.
So if the value is true, I'm saying value now equals false.
So is equal to toggle A.
And after that, it just gives
yes, whatever the final value is, because now the indentation breaks. The value will just revert back. The arrow will return.
So working on the reference.
It's called a borrow. So it's called a storage borrow. So I borrow a storage area, which means only that function can manage that borrow right now. I borrow, I modify, return.
Okay, like Rust.
Exactly like Rust. The idea is from Rust. So one thing you might pick up is that Coco, for me at least, is the amalgam of different ideas. From Rust, Ruby, C, Go, Python. I've taken whatever I like from different programming languages that I've worked with in the past, put it all together, and this is my favorite. Like, it's like, for me, whatever languages, whatever I could make sense of that made sense for blockchains, we brought into that idea here, right? So storage slots borrowing, this is how you do a flip currently, right? So this is your final logic. So you guys can copy this over if you want, copy of whatever you need. So we're
You
done
have
with
like GitHub repo or something. From the-
For this, oh yeah, you can. Oh yeah, I forgot you can do that. Just go to github.com, and you should be able to go to GitHub Server Labs. GitHub.com/Server Labs. So GitHub.com Server Labs. Go to Cocolang examples. LABS. Enter. Yeah, it should be a Cocolang examples, and in that there's a Flipper example. And you should just go to flipper.coco and you should be able to copy that whole thing.
There
Go
will
up,
be
go up.
Okay.
Flipper. Flipper.coco. You just do come and copy that whole thing.
Whole thing, right?
I'll also copy it for consistency.
Well, it's got a lot of comment code inside it. Good.
So should we actually paste the whole thing?
Yeah, you just
might as
do
well.
Command A, backspace, Command V. That's it. You get all the comments also. Right? So okay, so we have the exact same thing to get set toggle. Instead of flip, it's called toggle in this, and the init and seed. Yeah. So these are like our functions from this everything we just talked about. We have a set as a local function. There's a little bit more comments that will help you through this if you need it. But now this is our final module, right? So this is a simple module. It's an extremely simple contract. And this, by the way, is the same contract that we just looked at in our, this Solidity code, right? So there's a constructor, takes a bool init value, right? So let me open this up in presentation view. Yeah. So there's a constructor, bool init value. That's equal to our init deployer. Sorry, seed deployer, not an init deployer. We have a seed deployer, right?
Okay.
It's like that. It takes an input value and just sets that value, right? And then they have a flip function, which is like our toggle function. They have a public function that's called get, and they have a set function, right?
Yeah.
They don't have an internal function because everything they just directly set the values. They don't have any protection around the state values. Notice that this value itself, for example, it's bool private value. It's not using underscore value. You don't know that it's a state variable. It's supposed to be best practice, but this is taken straight out of. I believe it's taken straight from.
Actually, the underscores will be with the internal variables.
They use it for state variables also, no? State internal variables.
For internal, the underscore will be there.
Internal state variable. Can't be bothered.
Then you'll have to follow a proper developer to actually understand all these best practices.
Yeah.
But it's a best practice. It can't be enforced.
yeah, it can't be
The
enforced.
compiler doesn't
If you're a bad developer, and then you're screwed.
Yeah,
screwed.
simple as that.
The auditor's
Compiler
time.
doesn't enforce jack, basically.
Right.
So now I have all this. Now since we have a Coco ready to go, to compile this, who can guess the command?
Build
Coco compile.
Flipper.
Coco
I'm
compile.
guessing.
That's it. Coco compile. That's all.
Okay.
The coconut file takes care of everything.
Of course.
What if there are multiple files? Like
It'll take care. That's why the module name is there, right? Every file has to have the same Coco Flipper on top.
okay.
So all the files in the same directory, Coco Flipper, they'll take all the files Coco Flipper, aggregate them, compile it,
Make a manifest.
and then make a manifest. And when I make a manifest, I get this. This is my YAML manifest. Try it now. You can just do Coco compile.
I think it's throwing up an error.
Yeah.
On line number 21, there's an extra space.
Line 21. I didn't have any issues.
For
But
me
there's
also.
a new line, unfortunately.
No files found for module.
So check your directory in your VS Code terminal. Are you inside the Flipper module wherever you are?
Yeah, I'm inside.
And just so. How do I do it?
Oh, it's a capital F, sir, not small f.
I've changed to capital only.
No
So
files
this
found
one is
for
the
me.
ABI.
No, but you copied from GitHub, no?
Yeah.
So in the coconut file you changed?
Yeah.
Coconut file has a capital Flipper,
It's capital only.
and then when you run, whatever are you getting?
No
No
module called
module.
Flipper. So your flipper.coco, go to the top.
It's not saved, sir.
Okay.
Your coconut, whatever you changed, didn't get saved. Now it's saved.
So this one is actually the ABI.
That's that flipper.yaml has now your ABI plus your bytecode also.
Where's the bytecode?
If you just scroll and see it. So go find scroll down. Go to find a element called routine. Scroll down a little. Give more link. Keep going. Right there. These are all the bytecode.
Okay.
So one thing I would suggest is if you head out to the coconut file, I hope this works. I know we just implemented this.
Coconut
recently.
file.
And if you go to the coconut file, go to target.pisa and change it from format bin to format ASM.
Format bin to
ASM.
ASM.
Yeah.
So what will happen?
So this will generate the manifest will look different, supposed to at least. Yeah. If you go to the manifest, now your manifest will, instead of having binary output, it will have assembly output.
If you run Coco compile again,
So just
We'll
scroll
have
down.
to run Coco compile.
Yeah, run Coco compile one more time. Okay, now just close your
format
terminal.
ASM.
We'll have to close the.
You don't have to.
and-
I'm just for giving you space. You can just
Assembly
scroll down.
module.
You'll be fine. Two fingers, sir. 2 finger scroll. Yeah. So you'll notice instead of anything, you have assembly instructions that you can read.
So these are the bytecodes.
These
No,
are
you
the
can go to
instructions, the
YAML.
individual opcodes.
File.
The opcodes, sorry.
Yeah, carbs, obtain, set field, LDP,
Yeah,
one,
or
they're
the
all
JSON.
opcodes.
I mean, you're compiling to JSON.
Right? So you can compile JSON, Polo, so you can generate the raw data that you send to the protocol directly with the Polo data, whatever.
So you can look at the executes bit and you can see that's the register code that.
So it's the manifest.
This is the manifest, the flipper.yaml you're saying.
Yeah.
But the thing you send to the protocol is not the YAML file, you'll send the Polo encoded version of it.
Okay, that manifest will encode it to
In Polo.
version.
Yeah,
and then
correct. So you can do that yourself. So in your Coconut file, if you change it from format YAML to Polo, it will give you Polo data. So in target.moi, there's a format called YAML. You change that to Polo, all caps POLO. And then you'll get a flipper.polo, and this is some raw bytes. You can't see, it's like a binary output. You can't read it.
Open anyway.
Yeah, it'll
With
just
a
give you,
text editor, yeah.
and it'll give you some random byte output.
Yeah.
Right? And you can generate a JSON, YAML, whatever you feel familiar with. When you pull it from the registry, you'll get it from YAML. JSON, because JavaScript is easier to understand. Cool. So now we have our flipper.yaml file, right? So this is your manifest that you essentially end up sending to the protocol after, of course, encoding the correct way that the SDK. So the SDK, we will add support for reading YAML files, JSON files, and it will encode and send. That it will take care of also. So if you have a YAML file, you give it to the SDK, it will take care of converting to Polo and sending. So SDK has all that built. And now the beauty is, now when you read today in the instruction, when we had the RPC call, we just say JSON. Tomorrow we'll add support for you to get the instructions in assembly form or in binary form or hexadecimal form. Right, so there are three possible target.pisa, right? We have three possibilities: ASM, bin, or hex. Right, HEX will give you hexadecimal strings.
Okay.
So it'll just give you simple long hex strings. But this is if you want to inspect the code, you want to understand what's happening, right? So for example, if you look at our set function, this is our local function, right? So you can see that this is an element. So if you look at a manifest, the top level, what we have first is we have a syntax for the manifest. Tells you that it's a 0.1 syntax. This is the syntax form for the thing. Then is the engine, which is kind of PISA, and there's no flags currently. You don't support any PISA flags yet. Then there are a set of elements. These elements define all your code objects, classes, routines, methods, whatever you do, they'll all get in these elements. So the first one we have is state, right? This here is called state, and inside the data, this spells it as persistent state, and the fields it has in slot 0, it has value. Type is bool, right? Similarly, now if I go to routine init, there is no accepting, there's no inputs, no outputs. And say executes, there's a binary instruction, it has no instructions. Pass has no code. Okay. And when I write my seed function, I also notice it has a dependency on 6 and 0.
Okay.
So it means it depends on 0, which is the state, and depends on 6, which is that set function.
Okay.
Right. So it creates a dependency between all the elements of which elements are required first. So it compiles them in particular order. If it detects any circular dependencies, it will fail the compile. Right. So there's all that rules. So this is a routine. Routine is a type name, and the kind is local. The kind could be local, invocable, deployer, whatever, right? So this is a local, accepts one input, value bool, returns nothing, executes. When it says obtain, it obtains the 0th value. So we're saying here obtains 0th value into register 0. And then I'm saying PSA, persistent state. I'm saying whatever is there in register 0 to this 0th slot. So 0th slot for persistent state is value. That's it. The opcodes are human readable effectively. Once you've understood the machine architecture, the opcodes are human readable and very efficient. To understand, I know the EVM quite well, and going through the decoding of the opcodes is quite headache. 20 opcodes to break the structure, figure out where the data is. All the decoding logic is handled at the VM level. I've just moved all that away because registers don't have to worry about that. You just say obtain. Obtain is doing all the work of figuring out where to decode, how much of the data to read, put all that.
But we as a developer never looked at opcodes. There's no need for actually to do that.
We are like DApp developers, right? So
Yeah.
don't need to go.
No, but I'll tell you how much of that is because you don't want to versus how much of that is because you can't, because you don't understand it because it's too complex. If you could, wouldn't you? If you could verify the code and verify that this is how I compile this, and is that really what the compiler is compiling? If you could verify that to some extent, wouldn't you want to know that I'm sure.
Obviously.
If I'm your end user, I might want to know, I can pull the manifest from your logic ID. You're telling me this is your application's contract. I might want to pull that code and verify that your code executes like you're saying it executes.
Sure.
I can't compile this back to Coco right now, but I can look at the raw opcodes and verify that you are not doing something dumb. You're not moving my funds without asking me. Right?
Yeah, sure.
So if I'm an end user and if I'm sophisticatedly advanced, the whole point of blockchain is verifiability and auditability, and you want to make sure that the code that runs on the chain is the code that is supposed to be running on the chain.
In Solidity, most of these auditors also don't look to the opcodes, I feel.
Yeah.
They actually look to the plain code and
Correct.
try to understand. But
And
it
that
would
means
be-
you're
it would
completely
be-
trusting the
So
Solcy. You're
opcodes,
completely trusting Solcy.
It's an entire new language itself.
yeah,
Correct.
For them.
and I feel for auditors, this part will be a lot more beneficial because
Correct.
they would be able to audit it in a proper way.
Because now you don't have to trust the Solcy compiler. You're trusting the
Compiled
the
code.
compiled output.
Yeah.
Right. So now the compiler also could have a what do you call that?
Vulnerability.
A
Malicious
vulnerability, right?
intent.
Someone could have released to you a default version or defective version of Solcy that compiles code and adds malicious code to a logic that you didn't even know existed. Right? These are attack vectors that really exist, right? It's not
Yeah.
that difficult to do. I can just create wherever you download Solcy from usually, maybe it comes along with Truffle. Truffle packages Solcy. What if Truffle doesn't use the official Solcy? What if Truffle ends up using their custom
Wrong.
version of Solcy where they start injecting malicious code into your opcodes? How do you verify that? You have to trust.
All these things have never been looked up in Solidity at least.
Correct.
Never-
I've always felt in the Ethereum ecosystem, a lot of people say like, chalega.
Chale.
Right? That's something I do not accept. So we went into the detail to figure out how this manifest works.
And this looks a lot more readable. Like it's
That's the goal, right? Because who can read bytecode, sir? But I can read the YAML files, quite sure. Right? If I understand the structure, it's quite straightforward. So today I can just look at the manifest and know exactly what the logic does.
I'm looking at the JSON file and I kind of get that because at least some JavaScript I've written in my life. So
Correct. Immediately it comes together. So now cool. So we now have a manifest, right? So this is generally what you do. So in our next call, like next time we do this, we'll do the JavaScript side of things where we'll deploy to chain. And one of our the guy who built the JS SDK, he'll come with us on that call, and we'll deploy to chain. We'll build an application to talk to this logic also.
Sure.
I mean, there are examples you can already go to. So if you go to the GitHub and you instead of Coco examples, you go to JS examples. There is an example of Flipper today that Shamir wrote, right? And this example has, so this is again our Flipper Coco file that we have, whatever we were just using. We store that in the bin and the output JSON that we use here. Okay, this is only required for deploy. We don't need that for later calls, right? So the full instruction Shamir has written here, like whatever we need to do. But you can write a full JavaScript code, and it has like a sun and moon thing. You know that Flipper thing. You just press it, the sun comes. If you click it, the moon comes. So you wrote some basic UI for that. So you guys can obviously use your own custom UI, integrate the JS SDK, the wallet signing, all that. Figure out to sign and send interactions. Today in the testnet, we don't currently separate view and get set calls. Every call goes through consensus. But in the final version, they will read calls will not go through consensus. If you make a call to get, it will just be it will convert into an RPC call, not into a consensus call, right? So we can avoid forming unnecessary consensus clusters because there are just simple read calls.
Yeah.
Right
Now it is actually forming those context clusters.
Yeah, even for view calls, it is forming the read. It's considering it as an interaction and creating a read call, and it's
That is why we have something called dgraph.
correct. Okay.
Yeah, like do you know about dgraph? Like
I know dgraph the company, but I'm not sure what you're talking about. Yeah.
so like it does pretty much the same thing.
Okay.
Like, because to handle the complexity in the case of Ethereum, like it gives a better indexing. Like we can.
So
Yeah,
okay,
we embed
but
the
that
data
is
and all
it's up to you to use dgraph to route it into this
And
that,
even the graph,
Exactly. Like here we don't even need to have a third
yeah,
party.
it's built into the protocol. The
Exactly.
protocol took care of that work for us.
Exactly.
so you're talking about the graph, right?
Yeah.
The graph.
Yeah.
Oh, like that. Okay, got it.
Yeah.
Okay, so now we have our compile manifest, right? So now we want to test this serve. I want to deploy it, test it, right? Let's before we talk about deploying to production, like or the testnet, right? We can do something locally. We have a tool for that called Logic Lab, and it comes built in with the Coco binary.
Okay.
Today it's a separate binary, but tomorrow it's going to be part of Coco. So today when you did Coco compile, you compile the thing. You can do Coco Lab and you can start the Coco Lab process, right? Today Logic Lab is built separately, so it comes as independent binary. But to start Logic Lab, first thing you need to do is set up a Logic Lab environment, right? So you just type Logic Lab, and then you just type Logic Lab init. Okay.
Logic.
Created a
Lab.
new directory.
Yeah, Logic Lab init will create a new directory called Logic Lab init.
Interesting.
Enter. Okay.
No,
Logic
no, no,
Lab.
no, 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 it's not right.
Yeah, so create a directory. So Logic Lab is like a simulation environment, right? So to actually start the interface, you have to do Logic Lab. You have to do init first, and then you can do start. Okay, so now we are in the REPL, right? Logic Lab REPL. So the first thing, like I just asked, like, what is the first thing you need to deploy logic? Even before you have a logic to deploy, you need to first have a sender. You need a user who can deploy the logic, right? You need a deployer first. So if you type users in the REPL, you will see that there is no users found in the current system, right? And that's why we created that Logic Lab init, by the way, because it's a database. It will store everything about the users you create now. So you can create a new user by just typing.
Centralized database.
It's right there in your system. So .logic.
It's a local.
It's just it's a local simulation environment, right? So if I want to create a new user, I just type register, and I can give it a name. So I'm just using register Manish, and it will create a user. Right? Enter. That's it. Register Manish.
I'll create Beam. So yeah, Beam created the address. Okay. So
Okay. So now when you type users, you will see the user that you created available.
Beam. Yeah.
Right. So now you have a user to use, but that guy is just a user right now. We need to assign him as a sender, and the way you do that is you do set designated dot sender, and then you just type Manish. Okay. Set designated as sender Manish. Okay, you enter, that's it. Designated sender is set to Manish. All right. So, and when you want to confirm who is the current designated sender, you can just do get designated sender, and it will tell you that the current designated sender is Manish.
Okay.
Right. So we have a designated sender. We have a user, and we've assigned that user as a designated sender. So whenever I send an interaction now, it's going to automatically use this person.
Go through this address.
It will send from this address.
How do you check the private keys?
So there's no wallet layer on this. It's just an address.
Like I'm not getting it.
So there's no private key wallet, all that created today. So today we just create a simulation account who just has an address.
Okay, it's just
So all those
simulation.
things will be there.
That will come later. For now, there's just a simple address. Tomorrow we will allow you to inject your full wallet store, or you can bring your full key store, and this simulation environment will also be able to talk to the actual protocol.
Okay, got it.
So you can talk to a local system simulation or to the mainnet.
Okay.
Using the REPL to send interactions, create accounts, and all that, you can do all that here. There are gas cost implications for that, so you need to have an account, you need a wallet. So at that point, so Logic Lab is in very early stage today. So this is all purely simulation. The entire chain state transition of the chain is being managed locally. We're
But
not running.
over the Babylon testnet.
It's not running on the network. It's not running even a MOI node.
Okay.
It's just creating a blockchain wrapper around PISA.
So it is being done in the local PC.
Locally, yeah.
There's no node also running.
Node
It's
also
just
running.
the node also is not running. It's just running a PISA.
Simulation.
It's running a PISA instance. And around PISA instance, we're creating users, logic objects, everything. And there's no there's no blockchain, there's no transacts, all that is not running. There's no interactions also. So a call you make will be just you'll take a logic and you'll make a call to the logic. That's all.
But the real stuff is already implemented or not?
Yeah, those are all there on the Babylon testnet. This is just a way for you to test your logic.
Got it.
Okay.
Without incurring
any gas costs. So you can simulate, you can locally test, right? So now you have a designated sender. Like now, the first thing you need to do is deploy the logic.
Okay.
To deploy the logic, first thing you need to do is compile the manifest, right? So you just use the word so you can just type help compile actually. Help compile.
Help compile.
Yeah, so it will give you like the help string for how to use the compile command. Okay. So if you see in the examples, you have to do compile the name of the contract you're trying to compile for. Flipper. So compile Flipper from manifest, open parenthesis, and inside that you do /flipper.yaml. Right? Compile Flipper from manifest /flipper.yaml. From locally, I have flipper.yaml file right there.
From manifest.
You can just see from here, sir. It's right there. The example string.
Okay. From
Same thing.
manifest.
Open quote, open parenthesis. Open quotes.
Missing.
It's the same thing.
Slash.
Okay.
No, it's not in jug. Your file is here. It's a file path.
Okay,
So
okay.
just dot slash flipper dot manifest. That's an example, right?
So here,
Dot slash flipper dot YAML.
dot slash flipper.
No, dot slash you need what, sir? Dot means local.
We need
slash.
better.
Capital F.
No, it's the file name, so flipper.yaml. You're just telling that create a manifest from the file that you have locally. Right? It's the REPL is running in your local environment, right?
For compiling also, like fuel is being consumed.
Yes. So that you can think of that compile as the cost to compile a manifest into a logic. It's a deploy cost.
Okay.
Right? And when you actually deploy in the Babylon chain, there'll be another cost of 100 to deploy it to the chain. So compiling the manifest costs whatever X fuel plus the actual creation of logic costs another 100 fuel. So it's whatever you see plus 100 for Babylon. Okay. So now when you do this, now it says compile. So you have a logic. So if you can just type logics in your thing, you'll see what all logics you have available in your lab. Okay. So the beauty now is you can actually exit the entire simulation and then you can come back right now and then everything is still, whatever you did is all saved.
So how is this happening?
It's all stored inside the dot logic lab directory.
Okay.
Okay, that logic that contains an inventory of everything you create. It creates a local session. It's not managing a database it's not managing a full blockchain node.
Okay.
It's just it's a simulation toy. It's not meant to be serious. Okay, so it's not going to be to production. It's just a way for you to test your thing. Now the beauty is now you know how much your compiled manifest costs. It costs 435. Now you can do a bunch of testing on it, right? So now you can do get logics dot flipper to get the information about the flipper. Get logics dot flipper. Right? So when you do get logics at flipper, the first thing is the module name, which is flipper. And then you notice right next to it is ready equals false. Okay, ready is false for now. We'll get into why.
You compile it as.
You have to use the name you used for the compiled object. Yep. Yeah. So inside this, you can see there's a name of the module. It says ready is false. We'll look into why. And it has an address. That's the address of the logic. And then there's an addition which is 0, right? Which means it's the 0th version of the first version. And if you notice, the logic ID has some characters, but notice the address is also part of the logic ID. So it has 0800005C. The 08 represents that the persistent state is true.
The persistent
State is true. Ephemeral is false. Interactor is false. Asset logic is false. Engine PISA is not encoded logic. And what is the hash of the manifest we have? It maintains all this in the logic object.
So we deployed.
This has been so the thing is in the actual chain, the compiling and deploying happen in one call called IX logic deploy.
Okay, got it.
But in the simulation environment, you have to compile separately and you have to deploy separately. That's why it's not saying ready. Because we only compiled, but we did not deploy it. So we have to initialize we have to call a deploy
but
call.
how then we got the address? Like without deploying.
It's a simulation, sir. It just created a random address, right? There's no chain. Right? There's no chain, there's no blockchain, it's a simulation where I just create a random address and I just assign it. Right? So I have persistent is true, and so the problem is because I have persistent state true, I have yet to call a deployer. Right? In our case, we have either the seed or the init deployer. So to call deploy, I do deploy flipper dot, and I can choose my method that I want to use, init or seed. You can use whichever you want. But for the sake of illustration, let's do seed. Right? And then you have to write it like you would actually make a call, but you need to give an input, right? We know C takes a value called initial. So you do initial, and the value is, let's say, false. And that's the call you make on it. Deploy flipper.seed. The value, that input value is called initial, and the value for the initial is false. And you make an in call, that's it. Execution complete. Fuel is 175.
Missing colon after key. Okay.
Done. Cost 175 fuel to run. Okay. Now when you run that get logics.flipper again,
Like this one was actually the constructor, right?
That's the constructor seed.
Seed.
Yeah, because if you look at our call sites, seed is a constructor deployer.
Okay.
And init is also a deployer. You can see that when you run.
Okay. These call sites are actually these endpoints.
Those are the endpoints that you have.
Okay.
So you notice that set is not there, the small set.
The small
Like
set.
I'm not understanding one thing. Like in case of Solidity, like whenever there is a constructor, in order to deploy it, we need that constructor.
Correct.
But here, like
We just deployed, now we need to use a constructor, no? So you did deploy, and you did deploy flipper.seed. Seed is your constructor.
But earlier, like we did not deploy, we just compiled.
Compile.
But that time, like we should not get the address, no.
That's what's in the simulation and in the real protocol. When you just in the actual Babylon, when you just deploy, you'll not be able to do separately. You give the manifest, it will generate everything. It will deploy, it will create the initialization, everything, and give you
At that time only we have to specify the constructor.
Yes, because when you make the deploy call, it asks for the call site and call data also.
Okay.
In our case, because we're in a simulation environment, I can't do both in one shot.
Mhm.
So I'm giving you the option to compile first and then deploy second.
Okay.
Okay.
Right? So compile will just give you a semi-ready logic. You cannot make any calls on the logic until you deploy a call.
But in Solidity, this constructor actually doesn't have to do anything with the address, right?
No,
the
because
constructor arguments.
you don't give a constructor in Solidity because there's no
Yeah,
multiple constructors. You just give call data.
Yeah. So like in case of like let's say we have ERC20 contract. So you have to specify. We can explicitly specify the name of the ERC20 token and symbol, and then deploy it.
Right.
Yeah.
Let me open this up. Right. So I go to Docs, MOI.Technology, go to Build, JSON RPC, Send Interaction, IX Logic Deploy. Right. When I do IX Logic Deploy, my parameters are basically so. Let's look at the payload. Yeah. So so type 8 means IX Logic Deploy. Right. I'm set some fuel price and limit. Sender is the participant who's sending it. And inside my payload, I have my manifest. This is my raw Polo encoded manifest. This is my raw Polo encoded manifest that we just saw.
And
The call site is Cedar, and the call data is this. Again, Polo encoded input.
Okay. When we deploy this.
When we deploy, we give it like this. So it fully deploys, and it gives me back a receipt saying this is the logic ID for that.
This is ERC20, right?
This is for, I guess, this is just some logic, sir.
Okay.
This is
any smart contract you want to deploy, you just have to take the manifest and put it in there. And this is the call site use. In our case, if we had compiled our manifest into this and we use the CD, so you can do this in logic lab, right? So when you have the logic like this, you can do, remember that manifest we have, so manifest.
In this case, manifest also has an address.
No, sir, manifest does not have, it's just that we have created a pseudo logic, doesn't really exist. But we are telling you that it exists. I've created the account logic already. I'm just telling you, you cannot use this logic yet. The simulation is not the chain, right? The chain, there's no chain. So I never created anything. The manifest is deleted the moment I make a logic. So when I compile, what I'm compiling is I'm converting the manifest into a logic object. That logic object only is stored on chain. In the real protocol, we store both the manifest and the logic. But in our case, we take that entire manifest, compile it into a logic object that the protocol understands. And that is the one we save in the simulation.
Okay.
So now once I've saved this logic object, the problem is if the logic has an ephemeral state. So because the problem is I may have person state, I may not have person state, I may make a call. I didn't want to fold the compile and the deploy call together. I could potentially do compile manifest with this dot call. I could say this, I could specify the call side also. So it becomes one call. But for aesthetic reasons, you can do compile first. And then in order to use it, you have to deploy it separately. Right? If it had no state, you don't have to deploy. You can directly start using. Or if you had an ephemeral state, you can just start enlist and continue using.
Yeah.
Right? It's just to simplify the commands. Otherwise, we could have a compile logic from manifest this with call side. So it'll just become a very long, lengthy thing because you're doing it in REPL. You're not doing a JSON API call, right? So in REPL, you want to maintain some aesthetic also. But anyway, so I can create this manifest here, and I can ask this manifest to be given to me as a Polo, and it will take that Flipper YAML file and give it to me the raw Polo hex string, and I can just use this in my JavaScript, right? So you can do this in JS directly, but the point is, for IX logic deploy or whether you're trying to invoke when you're making a logic call, right? Works the same way, right? The IX logic invoke is 9. The payload now requires the logic ID, not the manifest. Call side, call it, right? So now when you do deploy, you automatically get the logic. Right? Everything is created, compiled all in one shot. It's just in a local simulation, we had to make some compromises to make it clean. Okay.
So that Polo code will be like
generated by the SDK. SDK can handle that. If you give it a JSON file, it will take care of the rest. Okay. So, so we have a logic. So now beauty is after we wrote our thing, you notice there's a state here and the state has 0, 1. Because we did, what is the word for it? We used init, right? And we used seed. And seed set the value to a certain value. We said false, right?
Yeah.
0, 1 in Polo means false.
Okay.
Now, for example, I do, instead of deploy, I write invoke. Because now I'm using an invoke, I'm not a deployer, right? I can use the invoke command. And instead of flipper.seed, I'm using flipper.toggle. Right? There's no input. Toggle just takes. right? There's no call data. Enter this, execution complete. Now when I read the logic
Will be
state, it's
0.
02.
0, 2, 0, 1,
0, 1 is false, 0, 2 is true. 0, 0 is null in
Okay.
Polo. 0, 1 is true,
Okay.
0, 1 is false, 0, 2 is true. So so this is like the way you can simulate the logic. So you can write all the logics you want, and then you can pass the inputs. And now the inputs does not need to be, you don't have to worry about the Polo encoding. This just gives you a REPL to play, experiment, or what kind of gas cost I'm expecting, how much it takes to what all outputs I'm getting. Is my logic correctly executing? Is the code correct? Before you deploy the chain, you can try all that on Logic Lab. Is the purpose of this tool, right? So it just gives you a good place to do. Eventually, Logic Lab will be more. It will be directly integrated to Coco. It will give you more features. We're still working on all these things. But yeah, so if you want to just know what all possible you can do, you just run the help command. You can use register to create new users. So whatever you're seeing in green means it's another help command. So you can do help register, help compile, help users. It will give you more commands, right? So if you can compile and create a new logic, you can get, set, and byte modifiers in memory, config, designated values. You can convert manifests between different formats, invoke and deploy. You can perform deploy calls, invoke calls. Okay, simple stuff today. We have a lot more planned for Logic Lab as we go, but this is what you're available to today. Yeah, you can even change things like if you're dealing with big numbers, right? Like big integers, you can tell the Logic Lab how to print big numbers. So today by default, if I wanted to do what, so get config dot hex big, right? Hex big int, right? It will tell me that big integers are printed today as hexadecimal.
Okay.
I can ask it to, I can change this to become numeric.
Get config, set config.
Yeah, I just do set
It's
config.
obvious.
True. Now, sorry, set config equals false. And now my thing will automatically switch to become false now. So now anytime I'm printing hexadecimal number, hexadecimal big integers, it will get printed in with a raw numeric value.
Okay.
If I had kept it true, it will be printed as hexadecimal. So you'll lose the sign value. You'll only get the hexadecimal output. And you can apply this for big int and for hex bytes, I think. Hex bytes? Yeah, hex bytes. So when addresses, bytes and all come, they're printed as hex. But you can ask it to be printed as arrays. Numeric array. So there's all the formatting options you can have.
How do we define array?
Sorry, as in?
How do we?
If you want to use an array, you mean, okay, let's say, for example, you can just use memory. You can set memory variables to the logic level. Okay, so you can do get a equals 500. Okay, so the variable a.
I'm asking in Coco language. How do we define an array?
Oh, okay, sorry. Let's go.
Let's go back to flipper.coco.
Flipper.coco. Let's just assume everything about doesn't exist. Okay, which is writing me. I can have a state persistent, and let's say I want to have value. It is of type array of string. This is a array, not an array. If you want an array, you have to specify the size. Array means dynamic size. Dynamic array. Dynamic array is called a array in Coco. So this is a dynamic array. We call it a array. And then if you want a fixed size array, you just give the size. And if you want map, I think I already showed you, right? You can do map. And if you want to write classes, you can do class, person, and then you do field, name, string, field, age, U64. So I have two fields on it, right? And then I could have a method. Yeah. So when you do yield, you're just setting the value of one of the outputs. Okay. So you can either do yield like this, meaning you can do, so if you have multiple values, right? If you return, you can do yield one by one. Or if you want to return everything at once, you can do return. Actually, it's now not curly braces, it's parenthesis now. Return, okay, equals. This also is valid. If you want to return all the outputs in one shot. Okay. Huh? Okay. Yeah. So you can use yield to return one value at a time, or you can just return all at once.
How do we create an object?
For the person class. So when you want to create a person class, there's two ways to do it. Okay. So one is, let's say I have this function, I can just do var, because there's no nulls, right? So I can just do var p person. And this is valid. What the hell? I could do p dot age. equals 18. This is one option. Or if you want to have a constructor, right? So you could do this, or the alternative is also you can do p equals make person, which will create a blank person, also valid, right? You have to still do var p. This is unnecessary, but it's valid syntax. You don't really need to do it. It's just considered valid because this can be used for creating empty string also sometimes. Okay, and it's used for arrays mostly. It's meant for arrays and arrays, but it's valid for any data type. Okay, but let's say you want to have a custom constructor on person, right? You can implement that by implementing. So if you're familiar with Python, this will immediately click for you. You can do __ build. And you got to take self, and you can take a name, string, and age, u64. This is your constructor, right? And your constructor may you can say var, and this constructor has to return a value type because no pointers here, okay? So you got to do p person, right? So you have to first create a class object called var p person, and then you want to do p dot name equals name, p dot age equals age. And then you don't have to return it because so we don't have to do var p person, I just realized, because you've already declared p. And p dot name, p dot thing is already declared, right? P is already declared in the outputs. So in my do function, if I want a new object v, I can just do var p equals build person Manish, 24. Okay. And this build function will call __ build. And you can use that to also extend other protocol level behaviors, right? So I mean other language behaviors. So you can implement method __ len or method _ join. So where in join you can take self and then other of type person, and then you return a joined person. And then you can define the rules for how to join two people, right? So if you do that, you can have var p1 comma p2 person, and then I can have p3 equals join
of
p1 comma
P1,
p2.
P2. Yeah.
And this you can define what the join logic is. And here's the beauty. Let's assume you want to have an exception, right? So if you want to throw an exception right in the middle of your function, let's say all this is gone, right? So let's say I do func. I can just do func throw, and I can just say error goodbye, okay? Something like that. I can just throw an exception. This will just throw a string exception. But let's say I wanted to have a class exception, then I want some custom behavior. I could have a class called insufficient balance. And inside that I could have some fields if I wanted to. Field is balance expected. Both of these are of type u64. Right? So this is my field, and I can say I can define a method build on this. __ build. And what is inside this? I need a self. I need a x comma y, both of which are u64. Return to me insuf balance object, right? Insuf balance error. So I could have this build method, and then I could create. I just assume this code is written, right? Like I just set create a new object dot this dot that is equal x y, and then now instead of doing this, I could do throw build insuf balance. Oh, actually, a really good point for how to build object codes instead of using. I just thought of a new syntax for this, but I could say 500, 1000, right? So this is I'm throwing this. But in order for this to valid, for me to use insufficient balance as an exception, I have to implement.
Oh, okay.
And then this takes self and it returns a string. So if you implement this method, like this signature, _ throw self error string, then you could format that into things. So you could do yield ERR is, and here we have something called f strings, and Python has f strings. You support f strings also. So you can have this thing is saying insufficient balance, and you can say expected And then here you would do self dot balance. And then you do expected, sorry, self dot expected actual. So it would fill in the self dot balance value or whatever that variable values will get filled into that place, and it'll generate a string with that actual values. So it won't say expected self expected. It'll say expected expected 10,000, actual 500. So it'll generate that string. So when you do throw build insufficient balance and throw that output, right, it will generate that class object and then it will throw it as an exception. So in order for a class to be throwable, you need this underscore throw. Similarly, same principle, if you want an event, say class event, right? Assume there are some fields, just assume. You just have to implement emit, right? If you implement the emit method, then you can do emit. Emit is still like pending development, but you could just do emit and then you can emit event and then create.
In this case, for like every event, we have to create a class.
Same thing in Solidity, no?
No. Event, we don't have to create a class.
Like
You create an event called event. You have to define an event, right?
Huh.
And the class.
But like we don't have to create manually. Like it's.
You still have to declare that it's an event, right? Yeah, you just have to declare an event and you have to declare that it index. For us, because we have a class object and we have all these custom behaviors, you can just write a class, and that same class can be an exception and it can also be an event.
okay.
Right? You can. It's like Pythonic.
Like in that we have this error class as well and event class as well. So here this class actually handles the exceptions as well as
it's just a class. That class can become used as an object. So you can use it for data management, or you could use it for handling operations, build operations now, or you could use it to throw exceptions, or you could use it to throw events, or you could do both, or you can you could add a lot of capabilities to classes with these underscore methods. In Python, these are called dunder methods. In Python, you can take an object called person and you can do underscore add. And you can explain to Python how to use the plus operator. So I can just do P1 plus P2 equals P3. And Python,
like operator overloading.
They're called dunder or magic methods.
Operator overloading, I guess.
No. Operator overloading is the principle,
dunder.
but if you go all the way down, it's called dunder methods. So operator overloading is specifically for operators, but you can also do things for how to do dictionary get. Dictionary set and all you can define in underscore methods. You can do a lot in underscore methods. They're called dunder methods or magic methods in Python, but that's also something I inherited into this language again.
Like
Just
every good quality.
Every quality that I liked and I wanted to use in this language, I brought in as much as possible, as much as it made sense to also.
As the creator of this language, you're allowed to.
Yeah, exactly. Whatever, like I had like freedom on that part, right? Of course. Anyway, so that is Cocolang, guys. So we just got a high level overview.
Superb language.